I mentioned previously that the functional groups that an organic molecule have will be the sites at which chemical reactions can occur. And so we already saw an example of that when we talked about how carboxylic acids and alcohols can react to produce esters. We're now going to take a look at a couple more organic reactions and see how the functional groups are the active sites or the reactive sites in the molecule. We're first going to talk about the halogenation of alkenes, meaning that here we're going to take an alkene and convert it into an alkyl halide. The alkene is our functional group that we're going to start with, and this is a reactive site. What we can do first is think about what would happen if you were to add a halogen across the double bond. So we're going to see an example of a reaction here where we take ethene, and we've got the double bond here. That's going to be the reactive site. And you can react it with bromine, which is an elemental halogen. Now, what happens when you perform this reaction is you break the pi bond between the two carbons, and in doing so, that frees up each of the two carbons to make a fourth bond. The first carbon gets freed up to make a fourth bond to one of the bromine atoms from Br2, and that goes there. The other carbon atom is freed up to make a fourth bond to the other bromine atom in Br2, and so the second Br goes right there. So that's all there is to it. When you see a double bond and you react it with a halogen, you would break the pi bond and then add one atom to one of the carbons and add the other atom to the other carbon. There is a somewhat complicated mechanism by which this reaction occurs, but we're not going to talk about the step-by-step mechanism for it here in this class. If you want to see that, you can learn about that in an organic chemistry course. For the purposes of this class, we're just talking about recognizing patterns and being able to predict the products of reactions. We could also talk about what would happen if you were to try to add a halo acid across a double bond. This is another way that you can make an alkyl halide from an alkene. In this case, we're going to again start with ethene, and instead of reacting with Br2, we'll react with HBr, that's a halo acid. Once again, you can break the pi bond, and in doing so, you free up each of the carbon atoms to make a fourth bond. So the first carbon atom can bond to one of the atoms in HBr. I just chose to make it react with H, so we put a hydrogen atom there. And then the second carbon atom would then be free to make a bond to the other atom in HBr, right? In this case, it makes the bond with Br, and there we have that. When you go on to taking organic chemistry, if that's a class that you need, you could start talking about how things can get really interesting with a reaction like this and how you can control which atom gets the H and which atom gets the Br when you do the reaction. But for the purposes of this class, we're just recognizing a pattern once again to say that if you have a double bond in a molecule and you're reacting it with HBr, you should break the pi bond and add the H to one carbon and add the Br to the other carbon. And that's it. Let's talk about another type of reaction. Now we're going to talk about the oxidation of alcohols. First, we'll talk about what would happen if you were to react a primary alcohol. So we'll refer to this molecule, this is ethanol, as a primary alcohol because the OH group is attached to a carbon that has just one substituent on it. So that's what it means for it to be primary. The functional group is on a primary site, meaning there's only one substituent or one R group that's attached to it. Now, to see what happens when you go and oxidize this molecule, it's helpful to first draw in the implied hydrogens in the molecule. So I'll point out here that this carbon atom here has two implied hydrogens because there are only two bonds that have been shown so far. And so to complete the octet rule, there must be two bonds to implied hydrogens. Now, when you perform oxidation, you're going to remove two hydrogen atoms. We're going to remove this hydrogen atom from the alcohol functional group and one of the two hydrogen atoms that's on the primary carbon there. So when you perform the oxidation reaction, those two H's go away, and in doing so, you free up this oxygen atom to make another bond, and you free up this carbon atom to make another bond, right? Because when this H goes away, now carbon only has 1, 2, 3 bonds. It wants to make a fourth, and so it will make the fourth bond by making a double bond to the oxygen. Now, in doing so, you've converted the primary alcohol into an aldehyde. And just for the sake of being really careful in terms of the labeling of the atoms, so you don't get tripped up or confused, this H atom here is the red hydrogen atom that I had from up above that did not get eliminated, right? So this H is gone, right? Allowing you to form a double bond to oxygen, and there's that. This H atom is also gone. This is the H atom that remains. This is the H atom that is part of that aldehyde functional group that you have here. So primary alcohols can be oxidized to make aldehydes, but you can even further oxidize an aldehyde. So you could perform a second oxidation reaction where you insert an oxygen atom in here. So again, this H atom, just to label it, this H atom was the H atom that was originally from the aldehyde functional group, right? You inserted an extra oxygen atom in here, making a carboxylic acid. Now you might wonder, like, what's the relevance of this reaction? This is a reaction that happens in the human body. So when a person drinks an alcoholic beverage, the alcohol that they're drinking is ethanol. That is this molecule. And there are enzymes in your liver that oxidize the alcohol and metabolize it, right? Because if that didn't happen and the alcohol just stayed in your system, forever, you'd be drunk forever after drinking, something. And that would be really, really bad for you. And so you oxidize the ethanol first into ethanal, and that's kind of a molecule that doesn't make you feel very good. It kind of makes you feel a little bit maybe hungover. And then it can get oxidized further to make ethanoic acid, or we know this as acetic acid. It gets excreted from the body and, then it's over. But this is a reaction that happens in the human body. So it's nice to take a look at it and to be able to see how the reaction can progress as you perform these series of oxidation steps. Incidentally, the reason why you cannot drink methanol is because when your body metabolizes that, the methanol gets converted into methanal, or that's formaldehyde, and that's really bad for your body. And then it leads to a lot of difficulties for you, which is why you should never drink methanol. It's not, the methanol does have some toxic effects on the body, but the metabolism products of it also have some very toxic and deleterious effects on the body as well. However, it's not only primary alcohols that can be oxidized, we can also oxidize secondary alcohols. And so we'll take a look at an example of that here. This is a secondary alcohol because what we see is that the OH group appears on an interior carbon. This carbon is attached to two substituents, or to two groups, right? Here's one, here's two. That's why we call this a secondary alcohol. Now let's talk about how you could predict the product for the oxidation of this molecule. What we'll start by doing is adding in the implied hydrogen that's on the carbon atom attached to the OH group. In this case, there's only one hydrogen atom that's attached to to this carbon, right? Because there's already 1, 2, 3 bonds shown. And so that means there's only one more bond to a hydrogen to make a total of 4 to, obey the octet rule. Now, when we perform oxidation, we're once again going to remove 2 hydrogen atoms. We'll start by removing the hydrogen atom that's in the alcohol functional group, and then we'll also remove the hydrogen atom that is attached to that carbon atom there. In doing so, this carbon atom now only has 3 bonds, and so it wants to form a 4th bond, and it will form the 4th bond to oxygen, right? Because oxygen now wants another bond after you've taken the hydrogen away from it. So in doing so, you're now going to oxidize and form a CO double bond. Now let's think about what type of functional group this is. When you have a carbon that's double bonded to oxygen, that carbon atom is an interior atom, right? It's in the middle of a chain. We consider this to be a ketone functional group. And so we can conclude that secondary alcohols can be oxidized to make ketones. You cannot perform any further oxidation at this point. And so unlike in the case of a primary alcohol, you can only perform one oxidation step on a secondary alcohol. Lastly, we'll talk about tertiary alcohols. So here's an example of one. And let's talk about what a tertiary alcohol is. So we have our alcohol functional group, and the carbon atom that it's attached to is tertiary because it is attached to 3 hydrocarbon fragments, or there's like 3 substituents on it, right? Here's 1, 2, 3. So we call that tertiary. Now, in the case of a tertiary alcohol, let's think about what would happen if you were to try to oxidize it. So I'll point out that in the cases of both the primary and the secondary alcohols, we perform the first oxidation step by removing the H from the functional group, right? So there's an H in the functional group, but we also have to remove a second hydrogen atom that comes from the carbon atom. But this carbon atom does not have any hydrogens attached to it. Because there are no hydrogen atoms attached to it, there's nothing for you to remove, and so there's no way for you to free up the carbon to make an additional bond to the oxygen, right? Think about what would happen if you were to try to form another bond between carbon and oxygen here. You would end up making 5 bonds to carbon, and that violates the octet rule. And therefore, it is impossible to make a CO double bond. It is impossible to oxidize this alcohol. And so we just say for tertiary alcohols, there is no oxidation possible. Okay, so what are the take-home messages from this slide and from this discussion here? What you need to be able to do is predict the product of oxidizing an alcohol. And so what you'll need to do is look at the structure of an alcohol, determine if it's primary, secondary, or tertiary. If it's primary and the problem says that you're oxidizing it, then possible oxidation products could be an aldehyde or a carboxylic acid. If you're dealing with a secondary alcohol and the problem is telling you that it's being oxidized, then the only possible product that you could make would be a ketone, right? And you should be able to predict what the product is, because all you're doing is removing these two H's and then making the ketone functional group by making the double bond to oxygen. If you're told that you have a tertiary alcohol and they ask you what happens if you try to oxidize it, you would say no reaction occurs. So that's kind of the take-home message from this, is you're going to be able to predict what the product of the oxidation reaction is. We're not talking about the mechanism for the reaction or anything like that here. We're just talking about being able to predict the products of the reactions and to be able to see how the functional groups are the reactive sites in a molecule and how you can see common patterns in functional groups that allow you to predict the products for a whole host of different chemical reactions.